Hello everyone, I'm Shubhangi Kataria and I'm from Group 2 from EXTC and we are here to present our coursework project of the subject Microwave Engineering, role of microwave for improving medical treatment. As we know, humans are reproductive organ of technology and it is very important that we as a human develop technologies that help to build our medical industry. So we are here to discuss about microwaves and next slide, please. To talk about my group members, we have Ajita Rajkumar, roll number 1, Welton D'Souza, roll number 16, Shubhangi, roll number 21, and Merlin Tommy, roll number 29. This coursework is done under our teacher, Frida ma'am. Next slide, please. Over to
So,
you, Pete.
what is microwave? So, as the name suggests, micro, that is small, and the waves, that stands for electromagnetic waves. So, microwave is nothing but the study of electromagnetic waves. So, it is the study to design microwave circuits, components, and other systems. So, microwaves are electromagnetic waves with wavelength ranging from 1 meter to 1 millimeter, and the frequency ranging from 300 megahertz to 300 gigahertz. Microwave frequency is basically categorized into three bands, that is ultra high frequency range from zero point 0.3 gigahertz to 3 gigahertz, the super high frequency range, that is 3 gigahertz to 30 gigahertz, and the extra high frequency range 30 gigahertz to 300 gigahertz. There are many applications of microwave like the industrial and space, but in today's PPT we'll be briefly gonna study and discuss the application in the medical industry. So what are the issues regarding or the disadvantages of microwave? So microwave has a negative impact on us as well as on the environment, since microwaves are produced by certain components and these equipments are made from non-renewable sources. It has a direct impact on the environment. Also, the disposal of microwave is one of the greatest source of environment. In this process, we need to dispose it incorrectly, as well as microwave has a greater or a negative impact on our health as well. It causes brain diffusions or brain structural damage. Over to you, Shubhangi.
It is important to discuss about the history and how it has come. So let me take you a little back. And in March 1971, Dr. Raymond Damadian published an article on tumor detection by NMR. NMR is basically nuclear magnetic resonance. So this was the most first discovery. Nobody ever thought about it. So this discovery was about that there are two T1 and T2 NMR signal which are coming back from tumor, and it was easily differentiated with respect to the other normal cells. So further, after few years, there was a technology called MR spectroscopy. So in this technology, the scientists were able to distinguish between benign cell, which is a tumor cell but non-cancerous, so it is safe, but and the malignant cells, which is cancerous, and it can be harmful for the body. Further, after 3 years, Dr. Paul Lauterbach, he wrote an article on image formation by induced local interaction examples employing nuclear magnetic resonance. So in this, he used isotopes of hydrogen. So there were two water, that is H2O and D2O. So he tried to distinguish them and plot them on a screen, and it was not that great image, but it was definitely a start of the basic of MRI. Further, this technology was called zygmatography, and after few years, zero point 0.8 Tesla to 1.2 Tesla was given into a machine for a human body. It was divided into X, Y, Z coordinates, which will give us a 3D image. And in Z direction, our magnetic fields were applied. So what this image used to do is it used to divide the voxels into two parts, that is black and white. Black being the strong signal and white being the place where there is no signal. So this might sound a little complex. So we have a video here, which we'll be showing right now. Next slide, please. In this video, there are a lot of animations. Let us see this.
'71 edition of the journal Science. The first to propose the use of NMR to diagnose disease in humans was Dr. Raymond Damadian, who in the March 1971 edition of the journal Science published a short article entitled Tumor Detection by Nuclear Magnetic Resonance, in which he suggested that the NMR signal from tumors in the body could be differentiated from normal tissues and therefore could be detected. His original concept was not to make an anatomic picture, but to build a detector large enough to accommodate a human, perform a whole body NMR, and look for a characteristic T1 and T2 tumor signal that would suggest you have a malignancy somewhere in your body, sort of a quick screening tool for malignancy. While Dr. Damadian's tumor detector never came to fruition, we do use MR spectroscopy in conjunction with a standard MR image to help distinguish benign from malignant processes in the body. To make an NMR picture, or MRI as we know it today, we have to be able to localize the signals coming from the sample or tissues in 3D space. The first to propose a technique to do just that was Dr. Paul Latimer. In the March 1973 edition of Nature, Latimer published a brief article entitled Image Formation by Induced Local Interactions, Examples Employing Nuclear Magnetic Resonance. In the article, he describes a technique using magnetic gradients to identify the location of two 1 millimeter capillary tubes filled with water, both of which were submerged in a larger 4.2 millimeter tube filled with heavy water. Heavy water has the symbol D2O because the hydrogen atoms of heavy water are isotopes of the standard chromium configuration with one proton in the nucleus. The deuterium atom, on the other hand, contains a neutron as well as the proton, which limits the spin of the nucleus and, therefore, does not give a good NMR signal. Latimer placed his apparatus in the high-field NMR magnet as shown and developed a technique to identify the actual origin of the NMR signals from the standard water. This is the image produced, very primitive by today's standards, but clearly shows the location of the two capillary tubes of standard water. Latimer called his technique zoopmatography from the Greek zoopma, which means that which is used for joining. To show you how we make an actual MR picture, we're going to move our perspective of our spins from the side to the top and represent each movement simply by the net magnetic field rotating around the axis. Remember that the Laue-Moore or resonant frequency of our spins is determined by the strength of the local magnetic field. When we first get into the MRI machine, a superconducting magnet creates a near homogeneous magnetic field from one side to the other that determines the strength of the MRI machine. Common systems are 1, 1.5, and 3 Tesla in strength. There are 3 sets of radiant magnets in the MRI used to localize locations in 3D space: the Z-axis, X-axis, and Y-axis. To select a particular slice of tissue body, we can turn on the set of electromagnets along the Z-axis that create a magnetic gradient from head to toe. We now put in a radio pulse with a frequency that will cause the desired area to resonate as described earlier. We have now selected our slice through the body. Because the local magnetic gradient is homogeneous, all of these net magnetic moments of the slice are in phase, spinning together in sync, and can't be distinguished from one another. To further localize these magnetic moments and their signal strength, we have 2 more gradients that we can use to isolate the source of the signals. The first gradient is called the phase encoding gradient. To demonstrate the effect, we're going to slow down our net magnetic moments. The phase encoding gradient is briefly turned on, creating a gradient along the y-axis in this particular case, resulting in the magnetic moments at the bottom of the gradient to slow down, and the ones at the top where the magnetic field is higher to speed up. The gradient is quickly turned off, and the spinning magnets return to the base frequency, spinning at the same rate, but they have now experienced a phase shift in the y-axis, which we can use to localize the spins in the y direction. We then tune our system to focus on a particular phase in the matrix and use our third gradient in the x direction to definitively localize each of these signals in the selected row. This gradient again causes the spins to the right to slow down and the ones on the left to speed up. This frequency encoding gradient remains on while the signals are recorded. Now each of the signals has a unique phase and frequency which can be localized in 3D space. The whole process is repeated with each row, localizing, in this example, in the y direction with the phase encoding gradient and in the x direction with the frequency encoding gradient until the entire matrix is complete. Each of these squares or voxels are assigned a grayscale value corresponding to the strength of the local signal, by convention, white being a strong signal and black being no signal at all. In this simplified example, our 4x4 matrix doesn't look like much, but a standard MRI with a 256 by 256 or 512 by 512 matrix will provide exquisite anatomic details of the body.
So as we have seen in this video, that the output of the water experiment, the deuterium, the output was pretty much clear where the vessels were kept. It was slightly darker. And similarly, now we have seen the movements of the magnetic fields when the X and Y axis were operative. So now let us talk further in this presentation. Over to you, Merlin.
Propose the use of
So applications of microwave energy in medicine. So here first we are going to see the application that is MRI, that is magnetic resonance imaging. So it is basically a medical imaging technique that uses a magnetic field and a computer generated radio waves to create a detailed images of the organs and tissues in the body. So it is also helpful to detect a variety of conditions that include problems of the brain, spinal cord, and so on. Next slide, wait. So this is a video which gives us a basic idea of what is an MRI and what are the various conditions it detects. Yes, start the video.
Magnetic resonance imaging, commonly known as MRI, helps doctors find, watch, and treat medical problems. MRI uses very strong magnets, radio waves, and a computer to make pictures of the inside of the body. MRI pictures are more detailed than those made with other methods. There are many reasons to have MRI. MRI may find bleeding, such as bleeding in the brain, brain changes, as in stroke, problems with your back, such as a herniated disc, and an injury inside the body, such as a torn anterior cruciate ligament. Before MRI, you will remove all metal objects.
So as seen in this video, it is said that MRI gives us a clear images of the body parts that cannot be seen with an X-ray and CT scan or an ultrasound. So over to you, Ajita.
So microwave ablation is another application of microwave in medical science. So microwave ablation is basically a procedure in which it uses microwave to heat the cell and to destroy the tumor. So like I said, it is a method of thermal tumor ablation where the tumors are heated to damage the structure and the proteins of the cell. It is a destructive tool for abnormal tissues we are heating by the microwave. So the first success of microwave ablation therapy was found in hepatocellular carcinoma. It is basically a liver cancer. As you can see in this diagram, we can see a healthy liver and a liver cancer. So this is the condition of hepatocellular carcinoma. So in order to remove this tumor, this liver was exposed to a 2.45 gigahertz microwave with a wattage of 80 to 100. This microwave ablation was not just effective on liver, but it was also effective on kidney, lung, and bone. And majority of the studies have resulted in no recurrent tumors. As we know that tumors, it generally keeps recurring. So that is an advantage of microwave ablation. Next slide, please. So this is the microwave ablation schematic. So in this we can see a needle-like antenna over here, and the shape of the antenna is just and the antenna design, it determines the tissue heating pattern and therefore impacts the ablation zone size and shape. We can also use other design like monopole, dipole, and slotted antennas based on the organ, like where the tumor is located. So coming back to the schematic, so this and microwave antenna is made up of an applicator shaft that has a temperature monitoring. So as we know, we are going to heat the tumor, so we need to have a temperature monitoring because we are going to kill a tumor inside your body. So definitely we need to monitor the temperature. And when we are going to heat the tumor, we also need a cooling system supported by it in order to prevent burning. So this is the entire structure of this is the entire schematic of microwave ablation. Next slide, please. Please play the video. So this is how the animation of a microwave ablation, where we can see that we can see a liver with that white portion is the tumor, and once the equipment it starts shooting the microwave, we can see it is getting heated up. Once it has killed the tumor, it will start cooling down. So that black portion is basically the cooling down of the like how it is cooling down the tumor, and this is how microwave ablation happens. Uh, Next slide. Despite the success of microwave ablation in liver, lung, kidney and bone, the fact that this has not been it is not practiced as much as other methods, because one is that equipment needed to perform the therapy, and we need people who are well versed with this with these techniques, and along with these is the ablation therapy. Obviously, each and every method has an another competency like kind of thing, and here we have radio frequency ablation therapy, which has similar kind of a result, but microwave ablation has an upper hand because microwaves produce higher temperature with shorter ablation time and have a smaller heat sink effect. And like not the microwave and the radio frequency ablation, if we increase the usage of both these techniques, we can reduce the cost and time needed to treat all these small tumors. So this was microwave ablation. Next slide, please. Over to you, Merlin.
Microwave imaging. So before this, there were earlier other clinical imaging and detection modalities used for breast cancer detection, that were X-ray, mammography, magnetic resonance imaging, and ultrasound scanning. So the problem with mammography was that it used to create high false negative and high false positive results that can prove to be emotionally disruptive to the patient's life. In ultrasound, in ultrasound, it used to exhibit low resolution, due to which it was not able to distinguish between the malignant, that is non-cancerous, and malignant, that is cancerous breast tumors. Also, in testing using MRI, it was relatively expensive. So due to this various reasons, microwaves imaging has been researched as an alternative to X-rays and ultrasound screening. So microwave imaging is an appropriate alternative as it is low cost. So imaging techniques are used due to detect the malignant and benignant tissue. So due to higher water content in cancer cells, the dielectric properties of the tissue differs when exposed to microwaves. So utilizing the microwaves for diagnosing breast cancer needs further research. Despite the nearly 40 years of research in microwave breast imaging, there are still many limitations that can prevent a commercially available device that include inappropriate algorithms and sensors. However, with wider clinical trials, microwave imaging system may be feasible in the near future. Next slide. So these are the certain advantages like alternative to X-rays and ultrasound screening, low cost, harmless, and also easier to perform compared to the current methods with higher sensitivity. Next slide. Over to you, Welton.
So these are the certain references we have chosen to make this PPT and get the info. Thank you. Have a nice day.